In this lecture, we are touching on the term hashing. According to the Wikipedia, and that is a general definition, a hash function is any function that can be used to map data of arbitrary size to data of fixed size. The values returned by a hash function are called hash values, hash codes, digests, or simply hashes. I would say let's see an example. The easiest way to do hashing is by having a hash table. So we could, for example, hash names to integer values. John Smith could be mapped to 02. Lisa Smith could be mapped to 01. Sam Doe could be mapped to 04. And Sandra D could be mapped to 02 as well. And that would represent a collision because John Smith is already mapped to 02. Hashing is often confused with other very similar topics. For example, checksums, fingerprints, or lossy compression. Those are all very similar and they maybe overlap, but they are all different and they have different requirements. Let's look at some use cases of hashing. The first use case of hashing are hash tables, to quickly look up a data record, for example. This is very similar to caching, which is another use case where the hash is used to build up a cache for large data sets in slow media. Hashes can also be perfectly used to find duplicate entries in large data sets. And lastly, hashes are used to protect data with cryptographic hash functions. Hashes must meet some requirements and they have some important properties. Now let's check them out. A hash procedure must be deterministic. That means the same input must always produce the same output. A hash function should be uniform, which means that a large amount of input data should be evenly used to produce the output, not just the first few bytes. It is desirable that the output has a defined range, meaning the output has a fixed size. And especially in cryptographic applications, it is desired that hash functions are non-invertible. That means that given an output of the hash functions, it is not realistic to reconstruct the input. Then there is a vast amount of hash functions available. From universal hash functions such as the Zobrist hashing to non-cryptographic hash functions such as the Pearson hashing to what we know as unkeyed cryptographic hash functions, and that is like MD5 or SHA-1, 256, 512 or SHA-3. SHA-3 was initially also known as KZAC, which is used by Ethereum. The final implementation of SHA-3 differs from KZAC. So SHA-3 versions of Ethereum is the SHA-3 KZAC implementation, while the official one from NIST does a different input padding. Internally, they work exactly the same. In case of Ethereum mining, Dagger Hashimoto hashing is used. And this tries to satisfy two goals. The first one, it is ASIC resistant. That means that typical specialized miners for Bitcoin mining won't work with Ethereum. And it should be possible to verify blocks with light clients. But that's all way too detailed. You're probably more interested in Ethereum development. Mining is a completely different topic. Now, here's your takeaway. By now you should know that hashing is mapping any arbitrary large data sets to a fixed size. It is deterministic, which means that the same input always produces the same output. And especially for cryptographic use cases, realistically, it should not be possible to reproduce the input given the output.